Okay, so now let's examine this series. And this series, the terms of this series would look like this. The first term would be the difference 1 over 1 minus 1 over 1 plus 1, or 1 half. And that would be the first term. And to that I would add 1 over 2 minus 1 over 2 plus 1, which is 1/3. And to that I would add 1/3 minus 1/4. And you'd continue in this fashion to the term 1 over n minus 1 over n plus 1. And this would be um, the sequence of partials. This would be a partial sum. Actually, this would be the nth partial sum. This would actually be the nth partial sum. And look what happens with the nth partial sum. Um, this term here cancels this term here. There's a negative 1/2 and a positive 1/2. Here there's a negative 1/3 and a positive 1/3. So each term of the series of the sequence that forms this partial sum cancels the term right before it, the part that you're subtracting off. So for instance, this term here, the 1/2 cancels the 1/2 in the preceding term. The 1/3 here cancels the 1/3 in the preceding term. The 1/nth here, 1 over n here, would cancel 1 over n in the preceding term, but there's nothing that comes after this one. So after all is said and done, everything cancels except for the 1 and the 1 over n minus 1. So it turns out that this partial sum is just 1 minus 1 over n minus 1, where n is the partial sum that we're looking at. We're looking at the nth partial sum. So it turns out that the sequence of partial sums, would equal this sequence, 1 minus 1 over n minus 1. And if we want to know if this converges, all we would have to look at is the limit. And we look at the limit as n approaches infinity of the nth term of that sequence, Sn, which would be just this limit, the limit as n approaches infinity of this thing, 1 minus 1 over n minus 1. And as n goes to infinity, you see that this limit goes to 1. So not only does this original series converge because the sequence of partial sums converge, so this original series converges, but the sum of the series is equal to 1. Now, this series is actually a special series. If you take a look over here to the right, I have the definition here of a telescoping series. And it says, note that B2 is canceled by the second terms, B3 is canceled by the third term, and so on. And you see there that the nth partial sum is equal to B1, which in our case was 1, minus Bn plus 1. So uh, in this case, these would be the B's. If you take a look over here, uh, this would have been B1, this would have been B2, and then here we had B2 again, and B3 would be this, and here would have B3, and this would be B4, and all the way down here, this one would be Bn, and this would be Bn plus 1, n plus 1. So you see, what we're saying over here on this side is going to be B1, which in our case was the number 1, right? And it's going to be minus bn plus 1, which would just be 1 over n plus 1. Oops, this should have been a plus. Made that mistake. These should have been pluses all the way through. There should have been a plus. I just all of a sudden changed it from plus to minus. Sorry if I confused anybody. But this is Sn, and the limit is still the same. All the information is still the same, but this should have been a plus sign. So there we have it. That is a telescoping series, and the telescoping series we have a definition over here. The terms cancel. So let's take a look at one last example here. Let's take a look at this series. It will be 3 over, oops, forgot my summation notation here. All right, this will be the sum from n equals 1 to infinity of 3 divided by n squared plus 5n plus 4. Now, this one doesn't look like a telescoping series, but let's go ahead and break this down into its partial fraction decomposition and see what it looks like. So let's factor the denominator. This would then equal the sum from n equals 1 to infinity. So let's get that. The sum from n equals 1 to infinity of 3 over, this would be n plus 1 times n plus 4 if you factor it. N plus 1 times n plus 4. Alright, so we get this for the factored form, and that's equal to the sum from n equals 1 to infinity of some constant, let's call it a, over n plus 1, plus some constant b over n plus 4. Now we need to find those constants a and b. So let's see what we get here. Find those constants. So I know that, let's break it down here. I know that 3 over n plus 1 times n plus 4 should equal a over n plus 1 plus b over n plus 4. What I'm going to do is I'm going to go ahead and I'm going to clear the fractions out. So let's clear the fractions here. I'm going to multiply both sides by the LCD, which is n plus 1 times n plus 4. The left-hand side becomes 3. The right-hand side, well, if I multiply this by n plus 1 times n plus 4, the n plus 1 would cancel with the n plus 1, and I'd be left with a times n plus 4. Then plus, if I multiply this one by the LCD, the n plus 4s would cancel, and I'd be left with b times n plus 1. So, now we're going to try to find a and b. First, I'm going to let n equal negative 4. If I let n equal negative 4, this equation becomes 3 is equal to, well, a times negative 4 plus 4 would be 0, because 0 times a is 0. But b times negative 4 plus 1 would be negative 3b, in which case I see that b is equal to negative 1. So I found the value of b. Now, let n equal negative 1. Well, if I let n equal negative 1, this equation becomes 3 is equal to, well, this would be a times negative 1 plus 4, which would be 3a. And negative 1 plus 1 would be 0, and 0 times b would be 0. So it turns out that a is equal to positive 1. So I found the values of a and b. Let's go back up here. That means that this fraction, 3 over n plus 1, times n plus 4 is actually equal to 1 over n plus 1 minus, because b is negative 1, minus 1 over n plus 4. So, coming back to this sum, I can rewrite this sum in this way, this series. This series can now be written this way. I know that the sum from n equals 1 to infinity of 3 over n plus 1 times n plus 4 is the same as the sum from n equals 1 to infinity of 1 over n plus 1 minus 1 over n plus 4. That ends a bit off. N plus 4. All right, so now I have this series that I am looking at. This series, let's take a look at what the terms look like. Well, the first term, when n is equal to 1, when n is equal to 1, this thing is 1 over 2 minus, oops, this should be a plus sign. I keep doing that. 1 over 2 minus 1 over 5. Yep. And plus, when n is 2, this is going to be 1/3 minus 1/6. When n is equal to 3, this is going to be 1/4 minus 1/7. Uh, when n is equal to 4, this is going to be 1/5. And I see cancellation. 1/5 minus 1/8. And these begin to cancel now. Here's a positive 1/5, and here's a negative 1/5. The next term is going to cancel the 1/6. It's going to be a plus 1/6, and there's a minus 1/6. So now this is where the cancellation begins. So 1/5 is the first thing that's going to be canceled, which means I'm not going to cancel the 1/2, the 1/3, or the 1/4. And this continues on like this all the way up to the term 1n plus 1 minus 1 over n plus 4. Continues on like that, and it actually continues on forever. Okay, so let's see. Let's see what we can do with this. All right, so this would be, if we just stop it here and we don't let it continue forever, this would be the nth term in the sequence of partial sums. This would be the nth term in the sequence of partial sums. This would be the nth partial sum. So here's the nth partial sum. And what I'm going to do is I'm going to rearrange this. I'm going to rearrange the nth partial sum in a bit. Let's see how I'm going to arrange it. Well, the nth partial sum, I see that there's a 1/2, and I see that there's a 1/3, and then I see that I can create with this term and this term something that looks like this. I can rearrange these because it's addition, it's all commutative. 1/4, and I can put the minus 1/5 here. And then plus, well, here's 1/5. I can put it at the beginning of a term, 1/5, and then a minus, and here's 1/6. Here's minus 1/6. I can use this minus 1/6. And then, since there's a positive 1/6 here, I know everything after this is going to cancel. So there's a 1/6, and then I'd have minus 1/7. Oops, minus 1/7 here. So I'm just rearranging the terms. I'm just rearranging the terms. 1/7. And this could continue on. Plus dot 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 plus, and then the last term here, I would have a um, this would be 1 over n plus 3 minus 1 over n plus 4. Now I know everything is going to cancel. I know everything is going to cancel beyond this, except the 1/4, the 1/3, and the 1/2. This is going to have a cancellation for the one behind it. This is going to have a one cancellation for the one behind it. The one in front of this is going to cancel this one out. So I'm going to be left with this sum. It's going to be uh, 1/2 plus 1/3 plus 1/4 minus 1 over n plus 4. Everything else is going to cancel. So, turns out that my sequence of partial sums, Sn, is equal to, let's see, that's 1/2 plus 1/3 is 5/6. 5/6, let's see, the LCD there would be 12. If I add a 1/4, 6 goes into 12, that would be 10/12, and 3/12, 13/12. 13 over 12 minus 1 over n plus 4. And of course, just like the other telescoping series that we saw, if we take the limit here, the limit, as n approaches the limit to see if this sequence of partial sums actually converges, this limit would just equal 13 over 12, because this would go to 0 as n went to infinity. So therefore, I see that this is also a telescoping series, and the sum of this series is 13 over 12.